here too. So again, me missing that day last week kind of threw off the plan. Talking with Fifth Hour, it sounds like doing the test after the long weekend will be the better option for everybody. That being said, I'm going to have some stuff for chapter 4 that we're going to have to do in between. But it seemed like everybody was okay with that as the compromise. So we'll probably do a little bit of chapter 4 stuff next time on Wednesday, and also probably leave you some stuff on that asynchronous day. Whether you put that off till after the test or not is, that's certainly a reasonable thing to do. Everybody cool with that plan, though? It's probably feels a little less hectic. Okay. 310 is what we're going to do today. So this is about linear approximation and differentials. Now the textbook's notation on this stuff, I think, gets really kind of unnecessarily confusing. So here's kind of the general idea. So if we have a function here, we'll call this our function f of x. And let's say we have some value here. We'll call that value a. That x value we'll call a. So this point here would be like the point a comma f of a. Right? Now we can write a tangent line for the curve at that point, right? The equation for that tangent line is going to be f of a plus f prime of a times x minus a. That's just the point slope equation for a line rearranged a little bit by adding the y coordinate over to the other side, but that's all that is. That's just the equation for a tangent line, right? Everybody's cool with this? Now, we can use that tangent line to approximate the values on f of x, as long as, or at least in a neighborhood around that value a, right? So look, if I look relatively close to a, that tangent line is probably going to do a pretty good job of approximating what my function is doing. Everybody agree with that? So that's why we give this tangent line, in this section anyways, we call this a linearization or a linear approximation. So I'll call that like some linear approximation. Cool with that? I think I want to do this real quick. I'm just going to change the placement of that stuff real quick. Ugh. I think I want it to be like here. It's going to make the picture I draw next a little easier. That's a little better. Okay. Everybody's okay with that, though? I'm just adjusting the picture because now I want to draw in the differential part. So let's say we have a second x value here, and we'll call that a plus delta x, where that distance between a and that value, well, maybe we'll just call it like a1 or something. That's probably easier. Or maybe we'll just call it b. That's even better, right? No subscripts necessary. Call that b, or just the difference from a to b, we'll call it delta x, right? Just like a change in x. Everybody's okay with that? Okay. So if I look at this point, then that's the point b comma f of b, right? Everybody agree with that? So if I look at this distance here and this distance there, that's like the change in y and the change in x. Okay. So in this chapter, the differential dy is going to be the same thing as our delta x. And if we take this point here, which is just the point, or when we've plugged b into our tangent line, it bothers me to no one that they need to do this, like during the school day, running these loud machines. So the difference between the y-coordinate for our a and the y-coordinate on our approximation, that's our differential dy. Yeah, so if I look at, again, this is like dx here, so that's like dy.
That dy is also down there.
Oh, I'm sorry. It's infuriating. That's supposed to be dx. My apologies. Yes. Thank you. Yep. Okay, so this is kind of what's going on, right? We're just talking about a linearization, which is all that is the equation for a tangent line. And we're going to use that to approximate values just by plugging those values into that equation for a tangent line. And we'll have this idea of differentials, which is just, we'll use to talk about the error involved in our approximation. We'll talk about how we do that here in a minute. You guys okay with that, though? Okay. So let's run through a couple of examples, similar to things you'll do in your homework. So find the linearization of f of x equals the square root of x plus 3 at x equals 1. And then use it to approximate square root 398 and square root 405.
Is it 3.98 or
3.98. So when we ask for linearization, what are we really just asking for? Yeah, the tangent line. And we're looking for the tangent line of this f of x at that specific x value. So to write the equation for a line, we need two things. We need slope and a point, right? So our point, we know, is at x equals 1. How do we find the y coordinate? Plug it into the f of x. Very good. So we have the point 1, 2. And then to find the slope, what do we need? The derivative, yeah. So we'll take the derivative of f of x. So I would think about this as, instead of the square root of x, I'd think about it as x, or square root of x plus 3, I would think about as x plus 3 to the 1/2. So that's a chain rule problem, right? The derivative of the outside is a power rule, where I just move the coefficient to the front, then subtract 1 from the coefficient. And then I also have to multiply by the derivative of the inside, which is, well, that's just 1. So my slope then is going to be f prime of 1. Which is 1/4. So y minus y1 equals m times x minus x1. And then just rearrange some things here. So there's my linearization. The equation of my tangent line. 1/4 x plus 7/4. Blake? Sure, go ahead. Now, we wanted to approximate square root of 398 and square root of 405. So I remember that the function I have is the square root of x plus 3. So square root 398 must be 0.98 plus 3. So that tells me that the x value there is 0.98. So the square root of 398 will be approximately my linearization with 0.98 plugged in. And when I type into my calculator, I get exactly 1.995. And just for grins, Pretty good, right? Pretty good approximation. If I do the same thing at 405, I find the x value is 105 and I plug that in, get 2.0125. And I'd expect both of these to be quite good approximations because 1.05 and 0.98 are both very, very close to 1, right? Which is what I use to build my approximation with. So again, the actual value for square root 405, quite good. In practice, before you had digital calculators, this would be how you take the square root of like some crummy decimal, is you create a function like this and build a linear approximation for it and use that. So the natural question should be like, okay, so I have this linear approximation that I can use and gives me a pretty good approximation, at least some of the time. Like, what is the, like, if my approximation has to be at least this accurate, like, how long can I do that for, right? Like, how big of an interval of values can I use this approximation on and still get a pretty good approximation? So that's kind of the natural next question. So let's address that with an example. We're going to use the same example that we just did. So say, for example, that we need our approximation at least that accurate, right? So like, what values of x's can I still use this approximation on and still maintain this accuracy? And anything else after that I have to build a new linear approximation for, right? Is basically what we're saying. Okay. So if I want my approximation within 0.5 of the actual, what am I going to do? Well, the actual minus my approximation needs to be what? It has to be less than 0.05. Or really greater than like negative 0.05. Everybody agree with that? Okay. So I'm going to try to solve this compound inequality now. Everybody's cool with that? You remember how to solve a compound inequality like this? Where we have like a lot of different x's floating around. Okay, so my goal here would be to separate this into two separate inequalities rather than treating it as one compound. Probably before I do that, though, I'm going to do some rearranging in here, and then I'll separate. The thing that I'm remembering or seeing is this square root symbol with an x underneath it, and then I have stuff without the x's, or without this x's without the square root. Do you guys remember how to solve an equation that has a square root in it? Way back from Algebra 2? The goal would be to get the square root part by itself. That's the first step. So what I'm going to do is I'm going to subtract that square root to both parts of my inequality.
Could you also add the other quantity, the x plus 7/4 to both sides, or would that make it more complicated?
It's probably okay, but you're going to see why I'm going to do it this way in a moment, because we're also going to do this graphically, and the part that I want to graph is going to actually come out of doing it this way. So I'm just kind of like doing double duty here. But no, there's not a good reason why you couldn't have done the other. Everybody's okay with that? Now I'm going to get rid of the negatives here by dividing everything by -1. What do I have to remember when I do that? Yeah, those inequality symbols need to flip direction. And then as a matter of style, I hate when inequalities are written this way where the greater thing is on the left. You know, I just would prefer to write it this way. And I might as well separate at the same point. Right? So this is basically the too small and too big, right? Like if 1/4 x plus 7 is less than the actual minus 0.5, then our approximation is too small. If the approximation is bigger than the actual plus 0.5, then we're too big, right? So I just put a little verbiage there to remind myself what's going on there. All right. Did I make a mistake, Alexis?
Is it 1/4 x minus 7/4?
Well, I divided everything by negative.
Right.
Well, the negative distributed, right? Because I had the parenthesis in front of it. I think I got it. Is that done? That's okay? Okay. Yeah, if you're not sure, like, feel free to ask. Like, I make mistakes. We all know this. We've seen it. I try to minimize when it happens, so it's not like, ooh, you got to rewrite the whole thing now, because Mr. Kulik dropped a negative sign at step 1. Yes, Jillian.
What do you mean by too small and too big graph?
Okay. So graphically, this needs to be above that, right? If you're graphing the two curves, the thing that's greater than needs to be on top.
Literally just y up big.
Yeah.
Okay, so
Yep. That's all we're saying, graphically, anyways. Okay, let's do this algebraically first, and we'll circle back and show you what it would look like to solve this graphically in a moment. Again, on an AP exam, you can't be guaranteed that you have a calculator to do this kind of thing on. So, like, I'm going to run through how to do it algebraically and not graphically also. So again, we're going to get the square root part by itself. So I'm going to add a half to both sides. What's 7/4 plus a half? It'd be 9/4. Sheepers creepers, guys.
Oh, no.
That guy right there. That's okay. Mr. Kulik's on it today. And we'll square both sides. So what do I have to be? Does squaring both sides mess with my inequality? No, right? That should be fine. And then I have to FOIL that out, right? So let's see, 16, 1 over 16, and that's going to be what, 9/8 x plus 81/4. What am I left with now? It's a quadratic inequality, right? To solve that, it has to equal 0. So I'm going to subtract x from both sides. So 9/8 minus 1 is just 1/8. And then 81/4 minus 3 will be what, like 69/4? Everybody's okay with that? Okay. How would I solve this then?
Oh, wait. So you did, sorry. You subtracted both, right?
Mm-hmm.
Perfect.
I mean, I wouldn't try factoring this thing. You got all these stupid fractions in there. What would you do? Yeah, use the quadratic formula. For sure. For sure. Guess what you get when you do that? No real solution. What is that telling you? Well, it tells you that a linear approximation is always fine. It's never going to get too small, right? Basically saying those two things never intersect. So it's never going to be too small.
But if you got two real answers for the plus and minus, those would be
Oh, depends.
Oh.
Depends, because we also are going to have to worry about the too big piece. And we have to worry about whether is it happening in between those two x's or on either side of those two x's. So like, not so fast.
Yeah.
Not so fast, unfortunately. But that's the right idea. Yeah. Okay. Same idea over here, right? Can I just do this? Right, same idea. And just end up with what we end up putting the quadratic formula in. Is that okay with everybody? You'll deal with it? All right, what did I have here? I have 1 over 16x squared minus 3/8x minus 23/16 has to be less than 0. And this time, when you use the quadratic formula, we do get answers. I get x is equal to negative 2.66 and 8.66. Now, how can I tell if I'm looking at, remember, we're solving an inequality. This is the solution to 1 over 16x squared minus 3/8x minus 23 equals 0, right? That's not actually the solution to this. How can I tell if I want everything in between those two x's or on the outside of those two x's? Well, let's just think about the picture, right? So here's the x-axis. Here's negative 2.66. Here's 8.66. When I draw this parabola, should it be opening up or opening down? Up. Why?
X squared value is positive.
The leading coefficient is positive. Very good. So it should look like this. Okay? We're interested in where that parabola is less than 0. Is that above the x-axis or below the x-axis? Below. So we're interested in this part, which is between those two x's. So inside that interval our linear approximation is within a half a unit of the actual answer. So pretty good. The tighter you want, or the more accuracy you require, the smaller that interval is going to get, right? Everybody agree? That should be kind of obvious, right? Jack?
So what that's saying is that there's no value is too small, but that this set of values is what is too big.
Correct.
Okay.
Yes. No. It's as long as you're in between those two values, you're not too big.
Yeah.
You're just right.
Okay.
If you have like -0.67.
Well, you couldn't get negative 0.67 because the function we're approximating is the square root of x plus 3. So like you couldn't have anything that small because you get a non-real number. Like -3 is the beginning of the domain for the function, so our linearization obviously can't go smaller than that either. I think what you're asking though is like, if I get an answer in both places, how do I reconcile that? Right? You take the maximum of the two minimums, and then you take the minimum of the two maximums. So if you have two sets of these inequalities that it has to be between, you have to take the bigger of the two small numbers and the smaller of the two big numbers, right? So that it's guaranteed to be in between both of them at all times, right? Anise.
So when you say, not you, the book,
Yeah.
like when it says accurate within a number like 0.5, is it always just that?
That this process that we're doing right now, yeah.
Okay.
Yeah. So let's look at what this would look like graphically, right? So if I'm going to do this graphically, I'm going to just be looking at this inequality. So those are the three things that I'm going to graph. So x plus 3 minus 0.5, or square root of x plus 3 minus 0.5. The linearization is square root of x plus 3 plus 0.5. Now, I'm not going to graph all three of these things at the same time because that feels like that's kind of just a lot of crap going on. I'm just going to graph this part first, the too small part, and see what happens. So this curved line is my, there's my linearization. Oops, I goofed something up here. Hold on a second. Oh, Mr. Kulik, look what I did. I put a negative symbol instead of a subtraction symbol. It's like that should have still shown up. Why did that not work? Okay, so there's my linearization. This is the line that's too small. Notice that my linearization is always above the too small line. So it's never going to be too small or inaccurate from the too small side, right? Everybody's cool with that? So that says, okay, all values of x I got to work with. Great. If I go and turn that one off and I look at the too big piece, so there's my linearization. Here's my too big piece. Notice that I'm only smaller than my too big piece in between this point and like this point. That's the two that I need. So I need everything in between those where you're less than the too big line. Before that, notice that you're bigger than the too big. Just a little piece right there. And then after that, you notice you flip-flopped and you're now above the too big line again. So you just use your calculator to find the intersection here and here, and then you're between those two intersections, which is a lot nicer than having to do the algebra, but can't guarantee where a question like this would land on an AP exam if we had a calculator, non-calculator section, because it's perfectly doable without a calculator. It's just kind of tedious. Is that okay, though?
So
Okay.
like on the test,
you would want to see that algebraically.
I probably wouldn't care, to
Oh.
be honest with you. I just want to make sure that you've practiced it both ways, or show you that it's doable both ways. Because again, like solving an inequality and like doing some of these Algebra 2 solving skills is probably not at the top of our head. It's like, how do I do this? So that's my major motivation for reviewing this, is just like Algebra 2 review. Blake.
So going down the actual algebraic steps that we took, so those values of negative 2.66 and 8.66. So like for example, on the non-calculator part of the calc of AP test,
You'd probably leave those as like an improper fraction,
okay, because I don't know how to
or a radical.
find, like, I mean, I know how to use like
the formula.
but
Yeah,
I don't
you
think
just
I'd be able to get that.
you just leave it as like an expression with a radical in it or whatever. Ideally, if it was in the calculator section, it would work out to be like a rational number, where it would like the square root in there be like the square root of 4 or something that you could simplify. They could reasonably expect you to simplify, right? Like if it was in the non-calculator section, they would arrange that so that those numbers were not dreadful. They were like a rational number at minimum, if not an integral number, where it all simplifies down to like, oh, negative 4 and 8, you know, like where it was nice.
Yeah, so you don't end up not
Typically in the non-calculator section, for something that's going to be like a tedious solving calculation like this, that it work out to be nice. Yeah, that's again reasonable question. Okay, everybody's cool with what we did here? So again, talking about accuracy in terms of using our approximation. Let's talk about these differentials here and kind of what the difference is between like dy and delta y. So again, let's just look at a couple of quick examples here. And again, I caution you at looking at the textbook explanations for this stuff, because I think it gets very symbol heavy and like a little hard to decipher what they're doing. But it's like not complicated, but they're trying their hardest to make it seem like really technical and really complicated.
Plus, they're acting as like they're saying compared to y.
Yes. Yeah. 100%. All right. So compare delta y and dy if y equals x cubed plus x squared minus 2x plus 1, and x changes from 2 to 0.05. So first thing we should note is that delta x, that's just the change in x's. That's really easy, right? Cool with that. Delta y is just the change in y's. So that would be f of 205 minus f of 2. Right? Where what's my f that I'm talking about here? It's this guy right up there. What's the easiest way to type that into your calculator? Yeah, type it into one of your y's. Actually, let's just use y1. It's just that much less crap I have to deal with later. Okay. So there's my y. So I'll do vars, y vars, function y1 of 2005 minus vars, y vars, function y1 of 2. So I have 0.71765. Oops. Pretty cool there. Okay. Now let's calculate dy. So remember, dy dx is just f prime of x, right? Which in this case is 3x squared plus 2x minus 2. Very cool there. If I treat dy dx like a fraction to get the dy by itself, multiply that dx over. Cool there. And dx we can treat the same as delta x. And you can do that throughout this section. Delta x. And we're going to do that throughout this whole section. And everywhere in 310, you can do that when you're doing a linear approximation. That's okay.
Was that d of delta? Is that?
Oh, sorry. Yeah. No, sorry. Yes. I wrote the wrong symbol. No. Yep. My apologies. You got it. You got me. D delta does not make a whole lot of sense.
Change.
Yeah, a lot of change, right? A lot of change. Everybody's cool there? And then we'll just evaluate this where x is 2 and delta x is 0.05. What's the easiest way to do that in your calculator? Math. N derive. With respect to x, use the equation that I already wrote in y1. Evaluate that when x is equal to 2. And then I'm just going to multiply by 0.05. How wonderful is that? Your calculator is very good at taking specific derivatives, derivatives at a point. Your calculator can do that. Use it. Right? I think I've shown you this before. But get some practice. Use it. So what do we have here? This is about 0.7.
Aren't those two values, is it 0.7.71765? Aren't those like the same? Like they're both being expressions of like the change in y, correct?
Yeah, so do you want to draw a picture of kind of what's going on here again? So we have, actually let's do it on the calculator, it'll be easier. Well, maybe. I'll do it here. Give me this thing. So y equals x cubed plus x squared minus 2x plus 1. Okay. And then I want the point 1, 1. Or I'm sorry, it was 2, wasn't it? That was the point we were using? Yes, okay, sorry. It's not that one. So 2 and then 9. And then we had the point 205, which I wrote down in my notes Okay. Oops. Yeah, that's not what I wanted to do. Grid range is what I wanted. So just do the -5. Oops. -5 to 5 here. And then we'll go like 0 to 10 or something. Okay. So there's that. Those are the 2 points that we're interested in. And then let's draw in our tangent line. So that would have been 9 plus, I didn't write that down, did I? Of course I didn't. I'll just do it the dumb way. 3 times 4 plus 4 minus 2 times x minus 2. Okay, so there's my tangent line through the point 2. We should do some zooming here. Do 1 to 3. And then, it doesn't save me much. All right, this is not working out the way I wanted it to. Let's go away. All right, so like this spot here, Blake, where we have like the horizontal line at y equals 2. Oops. I'm sorry, y equals 9 coming through here, right? And I have the vertical line at x equals 205 coming through here. So this distance from this intersection at whatever this intersection is down here to the point on our curve is delta y.
Okay.
Okay. The distance from that intersection down here to the point on our approximation is dy. So notice that dy is less than delta y in this case because the approximation is less than the actual function at that value.
Okay.
So this is not telling you anything about the accuracy of this. It's just telling you, yeah, it can kind of tell you like how close it is, but it's not like which one is better than the other. Well, they're measuring 2 different things.
Mm-hmm.
Neither one of them is an approximation. It's just telling you about our approximation. Now here's what you can get though. Here's what you can get. What we can do with this. So we can use these things to come up with like relative error and maximum error and percent error and things like that. Let's look at one more example where I'll do some stuff with that with something that numerically is a little bit easier to deal with. So let's say that the radius of a sphere was measured and found to be 21 centimeters. With a possible error of 0.05. And then let's say we want, what is the maximum error? Using this measurement, what is the relative error? And then we'd say, like, what is the percent error? Again, from using this measurement. So the maximum error in this case is just going to be the value for dV, right? So the volume of a sphere is 4/3 pi r cubed. So dV dr is equal to 4/3 pi times 3r squared. Or I can say that dV is equal to 4 pi r squared dr. So we have 4 times pi times 21 squared times 0.05. So 277 cubic centimeters. Would be my maximum error. So what that's saying is what would it mean if I measured something to be 21 when it was really like 2105? Right? That's kind of what it's kind of getting at. So the relative error then, that would just be the change in volume divided by volume. Well, that's approximately the same thing as dV over V. So dV we found was 4 pi r squared dr. The volume V is 4/3 pi r cubed. If I simplify that, that's 3 dr over r. It's about 0.007.
Okay. You okay? Yeah. Good. Can you explain the step that you took from in the what is the max error question from dV over dr to dV? Like how you made that simplification?
From what?
So in the what is max error, the math
Yeah.
that you didn't write under that, how did you get from dV over dr?
So 4/3 times 3 is just 4.
Oh, you literally, okay.
And then I multiplied both sides by dr,
Oh, just to get rid of dV.
just to move the dr, to get dV by itself.
Oh, okay.
Right.
Yeah, totally.
It's okay. And then if I want the percent error, well, that's just going to be the relative error times 100. Well, I mean, if you're asking to do all three of them, yes, for sure, it's like the easiest thing to do. If I ask just for the relative error or just for the percent error, though, it's like the same thing as the relative error. You know, I mean, it's only that easy when it's just the only thing you ask for, or when you ask for all three of them in a row or whatever. So again, like the calculus piece, pretty light to just like understanding what we're doing here, right? Is that okay with everybody? That's it for this section. So what do we have here? 1 through 7 odd, and 11, 17, 19, 25, 33, 35, and 37. So that's a pretty short little section. You know, what's that, like 12 questions or something? Yeah, it was not too bad. I did this one because it was like one of those where it's like, well, making sure I really understood what I was reading, since the book was trying to make everything like kind of more complicated than I think it needed to be. And the notation was kind of weird. It's just like, oh, okay, I got it.
So is that example pretty much telling us that the measurement that they found is really accurate?
Yes.
Okay.
It is that even with that 0.05 error, it's not really a big deal, right? Like that's a good, you're doing a good job measuring if that's the worst error you're going to get. Which again, sometimes that's tough to tell, right? Because you're using it to calculate a volume. Like how bad could that volume get with that error, with that much error on a radius measurement? Because you're taking that measurement and cubing it.
Yeah.
So sometimes it's not always clear, like exactly how that's going to affect, how that error is going to be transferred through or whatever. All right. We'll